sure? You're confident?
Yeah.
Good morning, everybody.
Good morning.
How is everybody today? Meh? Nice? Oh,
Sleepy.
that's good.
Sleepy.
How many of you have started assignment 1? How many of you have finished assignment 1?
Why did I do it?
Well, it's, there we go. Nice. Well, you know, it's not due for a number of days, so that's all fine. Well, we might as well get into it then. My somewhat ambitious plan in this lecture is to cover the remaining material in this set of lecture slides. We'll see if we actually get through all the way through it, but hopefully we'll be able to move through it at a decent clip. So, yeah, good. So, last time we were talking about union find, which of course is a graph algorithm in a course where we haven't covered graph algorithms yet. But this should give you the flavor of how such algorithms can work, how you might store them, how it doesn't have to be as complicated as you might think. This is kind of the flavor of algorithms in general a lot of the time. You don't necessarily need to complicate things in order to gain a lot of efficiency. Now, sometimes it's useful to complicate things to gain some efficiency, but often less is more, right? To quote Eugene St. Uxbury, a design is not perfect when there is nothing left to add, but when there is nothing left to take away. So, at any rate, so we were talking about our first of 4 variants of this, of the union find algorithm. We were talking about quick find. It's called quick find because it optimizes for, yes?
Finding?
The find operation, yes. So, we had gone through the operations here. We were just about finished. For those of you who are like, what the heck is he talking about? This isn't where we left off. We did have the makeup lecture over the weekend, and we did get a little bit further into this slide deck than we were on Friday. And incidentally, if you hadn't heard, the Friday session wasn't recorded, despite the fact that I handed the guy the camera. So, you know. So we, if you log in and take a look at the makeup lecture, the makeup live stream that we had on Saturday, the first half of that or so is setting down in permanency the material that was discussed on Friday. So, at any rate, so very quickly recapping. In order to do quick find, you store one array of identification numbers. The keys of this data structure are the site IDs in the network. The values in this data structure are component IDs. This works very well because you always start these networks off with no connections made, and the only way to add connections is through the union operation. In the initial state of this algorithm, this ID array, each element will be initialized with the site ID that's pointing to it. So, upon initiation, we set each value to the corresponding key, right? This makes a lot of sense because in their unconnected state, these sites are their own connected components. Remember that we've defined a single node that's not connected to anything to be its own connected component, right? So, by organizing it thusly, the find operation finds which connected component the site is a member of. Now, the component IDs themselves are somewhat arbitrary. We can construct them in any manner which is convenient to the algorithm. So that means that the find operation itself requires only lookup with an array. And, of course, what's the complexity of that? Constant, yes. I'm going to keep saying it, I'm going to keep asking it until every single person in the class says it at the same time, and then I'll stop talking about it. So that's fine. Connected is simply two find operations in conjunction with an equality operation, or an equality comparison, right? We are trying to find if two sites are in the same component. So we look up the component IDs, compare them, see if they're the same. Very, very simple. What's the complexity? Constant time. Thank you. So quick find is it's improving the speed of find all the way to constant time, which is as good as it can possibly get, you know, without violating the laws of causality. This makes union more expensive. Because we are basically doing a bunch of bookkeeping to keep track of which component each site is in, it is necessary for us to proactively change all of the component IDs throughout the entire ID array anytime any modification is made via union. So basically, it's like, what do you know? It's impossible to know how many or which of these site IDs will be pointing to a particular component. Thus, each one must be checked. So how long does it take to check or modify every single thing in a linear data structure? What's the complexity?
Constant time.
It's big O-N. It's linear. So, you know, while, you know, we often say that linear is, like, not bad, you know, like, compared to most other runtimes, compared to most other complexities, it's quite good, actually. If we can do better, we should do better. So, yes, yes, and yeah, so if we were to take our union operation, right, on 1 and 6, see, I got a real laser sword, right? So, if we're connecting 1 and 6, we examine 1, we examine 6, we've got component IDs 1 and 0, right? We need to trace through the whole array, changing every 0 to a 1, or changing every 1 to a 0. At this point, for the quick find algorithm, it is an arbitrary decision whether you're changing 1 to the first or the first to the second. It doesn't matter, it doesn't affect anything, right? We're going to find out a little later when we get into weighted quick union that this decision can be useful, but we need a slightly more complicated approach in order for it to be useful, basically. Any questions about any of that so far? Here's your Java implementation, which I'm going to just kind of gloss over. You guys should have gotten the impression of it from the slides. If you're interested, you can study this on your own time. Actually, one of the things, basically the primary thing I'm asking you guys to do in your tutorials this week is to come up with implementations for all of these without looking at the slides. I made a special version of the slide deck with all the code removed so that you could have a reference, so as not to contaminate your brain with implementations from the textbook, because it's a much more valuable exercise for you to just come up with it yourself, right? And it's not worth marks, so there's no temptation to cheat, right? Anyway, so with respect to complexity, this is more or less everything we've already said. Initialization is big O-N, nothing we can do about that. As we go through this, we'll find out there's nothing we can do about that one. Find and connected are both constant time. Union is linear time. However, let's also consider that we are adding connections one at a time via union, right? It's not just that it's linear, the union operation itself is linear time. You must also consider how many times that operation might be performed. Because we are starting off with an uninitialized data structure with respect to connections, any kind of network that we may wish to represent must be built up from scratch. That will require, at maximum, n calls to union, right? Now, obviously, if you actually make n calls to union, you have a completely connected graph with only one component. So, you could make the argument that, is it still useful to be able to have this diagram to determine connectedness, because everything is connected to everything else. So in theory, if you knew that, you'd just know that, right? But let's say your number of connections is like 60% of the total, right? That's still proportional to the total number of nodes, right? So really, we're talking about a network with m connections. The time complexity is m times n. But since m is some unknown proportion of n, right, it's some constant times n, you could say that what we're actually dealing with here is a quadratic, right, rather than a linear complexity. Does that make sense? Once you take into account the actual construction of the data structure, right? So, any questions about any of that? Yes?
Will you update the slides later on? Because it still says they go and work connected.
Oh, I must not have just, I forgot to upload it to admin. Could you shoot me an email about that? I'll do it as soon as I get back to my office. Otherwise, I'll forget again. Any other questions? So far, so good? Good. All right, so things are going to get complicated. Let's make things a little more complicated, shall we? So, now, let's consider quick union. So we are complexifying the find operation, and with that, we are buying a faster unionizing time, right? So, the memory footprint, shall we say, between quick find and quick union is the same. They both require one array of integers or identification numbers. The question becomes, what are we identifying? Right? So, in quick union, we are throwing out the idea that our keys are site IDs and our values are component IDs. In quick union, we are no longer keeping track of component IDs. Rather, we are connecting the sites to other sites via that array. All right? So every node will point to another node via this index. It's like pointers, but without the memory addresses, right? Nodes which are their own component, nodes which do not point to anything, will point to themselves. So in this manner, the initialization routine is actually precisely the same between quick find and quick union. You initialize both in the same manner. Precisely the same manner. Let me just see how much of the slides I just said. Yes. Rather than containing somewhat arbitrary component numbers, each element of ID is the site ID of another site in the same component. Specifically, each site points to its parent node. The links form a tree structure where the root node is self-referential. So we have a diagram here. So this is what we're now looking at, right? So if we have the array indices 0 through 9, this is what a network containing two components would look like. These specific two components. So you'll notice 6 is pointing to 5, 5 is pointing to 0, 0 is pointing to 1, 1 is pointing to itself. That's the root node. Right? So, fine. How many people have seen trees before? How many people have not? Okay. I will quickly review the basic nomenclature then, since it seems that pretty much everybody knows what we're talking about. So, the tree, of course, itself is a hierarchical data structure where each node has at most one parent and any number of children. This distinguishes us from binary trees. We're not talking about binary trees here, right? What makes a binary tree? Who can tell me? Yes?
Each node has exactly 2 children or 0?
At most 2. Yeah. So in a binary tree, each parent has at most two children, 1, 0, or 2. In a trinary tree, each parent has at most 3 children, etc., etc. These are trees with an arbitrary number of children, and as we're going to see, that's actually going to be a very useful property going forward once we get into the more advanced versions of this algorithm. All right, we'll use that. But yes, so a forest is a disjoint collection of trees, and also a pun, because why wouldn't it be called a forest, right? Any collection of trees is a forest, right? The root, each tree has exactly one node that has no parent, which we call the root. In this case, the root nodes are their own parents, which, is of course a temporal paradox, but, whatever. So, in quick union, root nodes are distinguished by pointing them to themselves as their own parent. In some other versions of, tree algorithms, you might see, the root node have a null pointer to its parent, and that makes it the root, some other distinguishing characteristic. In this one, the distinguishing characteristic is this little self loop. Okay? You guys with me so far? Good. So, okay, just a little bit more tree anatomy. A leaf node is any node which does not point to any other nodes, so it's a node that has parents but no children. A stem node is any node in the tree which does point to other nodes, so anything which has children is also called a stem node. The nodes in a tree are organized into ranks or levels, and the width of a level is the number of nodes in that level. This is important nomenclature because we will have algorithms which operate proportionally to the width of ranks in a tree. We will have algorithms which perform based on the total number of nodes in a tree, right? If we're talking about a binary tree, right? Anybody off the top of their head know how many nodes there are in the maximum rank of a binary tree with respect to the number of nodes in the tree?
Is it 2 to the exponent is the depth of the tree?
Other way around. It's log n. And that's going to be important because a lot of our logarithmic runtimes are going to be based on that property of trees. That's where big O log n comes from a lot of the time. So, and that might be a preview of upcoming attractions in this very lecture. So, any questions about this so far? Yes?
Does the parent node always point to the child node, or is it the other way around?
It depends on what you're, like, it's an arbitrary decision depending on the implementation of the algorithm that you're currently doing. You know, you can have, in this case, we've got parents pointing at children. We can have children, like in the quick union algorithm, we actually have children pointing at parents. You could have bidirectional pointing, which kind of makes the thing a bit more like a doubly linked list.
Right.
You know, it depends on what you want to do with it. Make sense?
Yeah.
Any other questions? The point is that people are pointing at people. Yes?
What's the difference of the leaf node and the stem node?
Stem nodes have leaves, but leaves don't have other leaves. Make sense?
Yeah.
Any other questions? Okay. So, for the find operation, right? We have to keep in mind that the find operation has not, like the API itself has not changed with respect to, this new implementation of the algorithm. Find still needs to do the same thing, which is it needs to return a unique identifier based on what component any particular node is in, right? So, the manner in which we have decided to do, the way this works in Quick Union, we simply step into the data structure at the point of the node we're trying to look up. We then follow the links back up to the root node. And the site identification number of the root node is our component ID for that tree. Does that make sense? So, find has been made a bit more complicated, right? So, imagine your worst case scenario for this operation, right? The worst case scenario is that every single node in the entire network is all in one big tree, and you have selected a leaf node of that tree on the longest branch, right? Now, the construction of these things is somewhat arbitrary. What's the longest possible tree branch? How many nodes does it contain? Yes?
10 nodes.
That's right. Because the construction of these things is arbitrary, you can have an actual linear structure. So trees are more general, a more general graph than linked list, for example. So like a singly linked list is a possible form of a tree in this iteration of it, right? So what's our worst case complexity for the find operation under this scheme? It's linear, which is a lot worse than constant time. But the next thing you have to say is like, well, how likely is the worst case scenario, right? It would take one exact sequence, it would take a very small number of exact sequences of union operations to produce exactly this tree, right? But before we get there, let's talk about what union is, right? Yes. So if find has become big O(n), what about connected? What's that? It's linear as well, yeah. Because while find has changed, the nature of connected has not. We're still comparing two possibly unique identifiers that have been found using the find algorithm, right? So find twice is 2 times big O(n), which is big O(n), right? Any questions so far?
It wouldn't be 2 times big O n, because if there was 2 trees, then it can't be n in a chain, right?
Okay. I mean, okay. Worst case scenario, right? There, and you're trying to find if those two are connected, right? So like big O then minus 1, which we usually drop the minus 1 anyway.
Right.
Make sense? So you have to be like the ultimate pessimist to be an algorithms person. Anyway, so that's fine. So let's talk about laziness and unionization. So the approach that we were talking about before, or quick union, was what we call an eager approach. The reason we call it eager is because it would do stuff in advance so that things down the line would be easier. This is in contrast to lazy approaches, which only do as much as is necessary in the step that you're currently in, right? So, union then. It's quite simple, really. You take the root node of one of the trees and have it point to the other, right? Now, technically, you could have the root node of the tree you're attaching to the other tree. You could have that attached to any point of the tree, right? But it is definitely worth your time to find the root node of the other tree and attach it there instead. Remember that there's no restriction on the number of children any parent node can have, right? And our find time is proportional to the depth of the longest branch, or whatever branch you're on. So you have a strong incentive here to have very short, very flat trees, right? So connect them up as high as you can, right? Make sense? Any questions about that? Good. So, any tree can become a subtree of another if its root node is directed to some node in the other tree. Therefore, union first finds the roots of both components. If they are the same, nothing further is required. Remember that we only connect things that are currently unconnected. Next, one of them is made to point to the other. Unification achieved. So, in this case, if we're connecting 5, 9, 5, 9, we find the root nodes 1 and 8, right? And we make one modification to the array. We change 1 from pointing to 1 to pointing to 8. That is one modification to the array. We don't have to walk the whole array. So, what's our complexity? Sorry? Let me just...
If you start with the call connected, the packet got connected, wouldn't that be linear?
Yes. Well, it's fine, right? It's all based on the find operation. Similar to, not only do we have to test to see if it's connected, so we have to invoke the connected algorithm anyway, which is linear, in the worst case scenario. This, once we've got the two sites, the two root nodes, all this is like setting the site ID, the component ID of one to the other, right? So that itself is a constant time operation. But what you need to do to find whether or not they're connected, that's still big O n. So we're kind of in an interesting scenario, right? While this is a better algorithm for unionization, that doesn't actually show up inside of the big O metrics. Not yet, anyway. We still need to do a few more iterations. It is a better algorithm because the constants will be much lower, but we're still in the same algorithmic class. In fact, on paper, in that respect, quick union is actually worse than quick find. But, we'll see that. So, this is a series of union operations which you can see starts from our initial state where all nodes are disconnected, right? If we union 4, 3, 3 becomes 3, that, we pop 4 onto 3, 3, 8, we pop 3 onto 8, like that. 6, 5, we pop 6 onto 5, like that, right? 9, 4, now this is a little bit more interesting. 9, like 4 is in this one, so we're using 8, and 9 is there. But you guys get the point? This diagram is mostly just for completeness. But, yeah? Question?
Can you explain the 9-4 one?
Sure. So, 9, 4. If you look, this is the initial state, right? 4 yields 8 as its root. 9 yields 9 as its root. We connect the two by making 9 point at 8. Like that. Because we're connecting the root nodes. We're not connecting, like, the root of 1 to an arbitrary point in the other. Make sense? Any other questions? That keeps the tree flat, which is desirable. So, good. And I'll skip the Java implementation. So, as I said, on paper, quick union looks, okay. Connected should be a 1 there. Sorry about that, folks. Quick union performs linearly across the board. But the problem, or like the reason it's a better algorithm, is it has the potential to do much better in the average case, right? If you think about union in quick find, you are absolutely required to check every single element of the array every time you perform union, right? So that is a very stable runtime result. In the case of quick union, you really only have that when you're in the bloody worst case scenario, right? Most of the time, in fact, perhaps the overwhelming majority of the time, you're going to be dealing with much flatter trees, right? And that's like, depending on the size of the algorithm, of course, the tree is not going to be a linked list most of the time, so you do a lot better than linear time most of the time. But, again, this is big O, so we're interested in the worst case scenario, right? So, note that quick union's union requires 2 calls to find, thus having at least as much time complexity. Although the worst case quick union performs worse than quick find, in the average case it's quite a bit faster. If only there were some way of preventing the worst case scenario. So this is part of the other reason that we're so obsessively interested in the worst case scenario. It gives us one particular point that we can start working on in terms of refining algorithms, right? If you can improve the worst case scenario, you improve the big O, right? So the question we then have, how might we go about improving this? So, in our worst case scenario, we have a roughly linear data structure, right? How do we prevent something like that from forming in the first place? What leeway do we have? What arbitrary decision are we making at this point, which we could improve this with? Yes?
Like how you union those nodes, you don't put one like down another one, put like parallel.
Mm-hmm. So, yes. Now, this particular data structure, in order to produce this under the old system, basically, you know what? I'm gonna like shorten it so I don't have to do as much rewriting. Let's imagine we had 3 nodes in a line, and then we had a 4th node, right? In order to extend this, we would have to connect this guy here, right? Now, at the moment, the decision of whether we're connecting this guy to this guy or this guy to this guy, that's currently arbitrary, right? If we connected it the other way, right, then we wouldn't have a linearization, we wouldn't have that linearization effect. We would in fact have this as a result, which, you know, is much better. Much, much better. So, the question that you must ask yourself, how can we know algorithmically which one of these we should connect to the other? There are a couple of ways of going about this, but both kind of operate on the same principle. Well, it's called weighted quick union. So basically, we want to connect it up such that the smaller tree is being connected to the larger tree, right? The smaller tree should always be the subtree of the larger tree. Now, the question then becomes, how are you defining bigness and smallness, right? Well, it turns out there are a couple of different ways you can do it. And it doesn't really matter, to some extent it's not hugely important what your concept of bigness is, so long as it corresponds roughly to the number of nodes in that tree, right? Like you can do the depth of the tree for size, you can do like the breadth of the tree for size, you can do the raw number of nodes in the tree for your size, right? Any one of those metrics would be fine. Personally, I think it's easiest to keep track of raw size because it's just a simple increment operation, or not increment, it's a simple addition operation anytime you connect 2 trees together. The size of the new tree is just the sum of the 2 sizes of the old tree, right? That's nice and simple. But yeah, so we want to keep track of the size of each tree, right? And then we want to produce more balanced trees by linking those trees with smaller sizes to trees with larger sizes, but not vice versa, right? So, how do we keep track of size? Anybody have any ideas?
Just have a variable that's assigned to the tree.
Variable assigned to the tree. How many variables would we need?
Just one at the roots. And
One for each root, one for each tree. And in the worst case, we have n trees because we start off in a state where every tree is its own, or every node is its own tree, right? So we should have an array that is the size of the number of nodes and keep track of the sizes in it. Right?
yes.
Right. So, in addition to ID, we maintain an extra array size to keep count of the number of objects in the tree rooted at I. So, union is modified so that you are linking the root of the smaller tree to the root of the larger tree as determined by the size array. You must also update the size array accordingly, right? As I said, when you merge 2 trees together, the size of the tree gets updated to the, the 2 sizes of the trees that went into it, as you might expect. But I do take your point though, which is at a certain point, like once we have a small number of trees relative to the number of nodes, or relative to the number of components, we are wasting memory. Yeah. I take your point. But it's kind of worth it for the constant time lookup. You know?
Yeah.
And, you know, we also talk about memory, like we can talk about memory complexity as well as time complexity, right? To keep two arrays, both equal to the size of the input, in terms of complexity, that's still linear complexity, right? Because that's like the constant factor again, you know? So as long as we're not like squaring the amount of memory we need, we're still doing okay. Make sense? Any questions? This is all this is all digesting well? This isn't boring, is it? No? Okay, good. Would you admit it if it were boring? No? Okay.
So Monday morning.
Well, so if we take a look at how weighted quick union operates, let's just pick a point in the middle, right? Let's pick the two. Let's pick the 5. Let's pick the 5-9 operation, right? So this is what we're looking at beforehand. We're unioning 5 and 9 together, right? This is the smaller tree. 3 is the root, so 5 gets connected to 3. Right? Make sense? And you can see that she is flat like the pancake. Eh? So, the question you might be asking yourself then, and I see I've made that mistake again, that should be a 1. The question that we ask ourselves then is, what is the worst case scenario tree in this new wave forming trees? Well, it's a little bit abstruse, but basically, your worst case scenario is a binary tree, right? So if you imagine the tree is being formed like from the leaves up to the stem, right? It's like you know. Well, at any rate, the worst case scenario is a binary tree, right? What's the depth of a binary tree relative to the number of nodes in that tree? It's log n. Therefore, we have improved the runtime of find, connected, and union, because union now only depends on the complexity of find. Everything depends on the complexity of find now. We've improved that to now logarithmic time, which, you know, going from linear time to logarithmic time means that you can process something like 10 million data points in something like 20-some steps. It's like 26 steps, I think. So it's like very strongly good, if that makes sense. Now you still need the linear time to construct the network, right? But you know, n log n is much better than n squared. Make sense? So, the worst case weighted merge is 2 trees of equal size. Right, so if you don't believe me that the worst case scenario is a binary tree, right? Imagine every merge you perform is merging 2 trees of equal size. That will produce a binary tree, right? So, the depth of the binary tree is 2 to the power of k with, the depth of a binary tree with 2 to the power of k nodes is k. So, so that's how we managed to squeeze logarithmic time out of this bad boy. Question?
So we're still constructing the weighted quick union. We're constructing the trees from nothing. We don't have to like start with a tree.
Correct. The initialization has not changed. If the initialization, so you could make the argument, right, that under quick find, it doesn't really matter how the network is initialized. So long as the component IDs are all, what they're supposed to be, then everything's fine, right? We've now, one of the things that we've, lost as we've gained runtime is the arbitrariness of the connection structure, right? We now expect the connection structure to be very specific and rigidly defined, right? Each one of the links in that network has become very, very important to be, maintained correctly and all the rest of it. So, whereas before, we could probably get away with an arbitrary connection structure being initialized if we were to initialize the data structure, we are now completely and wholly dependent on the union operation to construct the trees in such a manner that the properties we need are maintained. Make sense?
Yes.
Yeah. Any other questions? Yes.
Out of curiosity, since the weighted union is initializing an extra array, does this mean that the space complexity will be linear for the weighted union?
The space complexity is still linear for weighted union. You're just initializing two elements of an array for every input rather than one. Make sense? Yeah, that's still linear. It's just modifying the constant.
And for quick union, the space complexity would be constant time or linear?
For which one?
The quick union, the space complexity would be constant time?
No, both of them are still linear. Because you still, it doesn't matter if you keep two arrays or one array. If either of them are proportional to the number of inputs, then that's linear. Right? Exactly proportional. Good. So, all right. Weighted quick union with path compression. So we've got this situation where the worst case scenario is now a binary tree. Let's see if we can do something about let's see if we can do something about that worst case scenario, and maybe we can get an even better algorithm, right? So, the worst case scenario is a binary tree, but because this is not an n-ary tree, this is just a tree, there is no actual restriction on the number of child nodes that any parent node can have. Therefore, we might be able to modify our algorithm in such a manner that maximum flatness is achieved. Right? So, the question becomes, how do we compress the longest path? Right? Well, two questions really. One, how do we compress paths? And two, when do we compress paths? Right? So, any ideas?
You compress paths when they get over a certain threshold.
So test the size, and then when it reaches over a certain threshold, yeah? Well, that's one way to do it, but it requires too much thinking. So let's talk about when to do it first, right? So if we are to perform path compression, we need an algorithm that's walking the data structure, right? At the moment, the only algorithm we have, which is walking the data structure, is find. So we'd like to add path compression as a side effect of the find operation. Make sense? Because otherwise, we're going to have to write a bunch of loops and introduce ourselves into the tree anyways and just add a bunch of complexity. If you're already in there, just, modify things a bit, and that's fine, right? So, very quickly, there are two approaches two-pass approach, where you keep track of all of the nodes that you visit, and you just connect them all up to the root node at the end, right? That's one way to do it. The other way to do it is change each node to point at its grandparent. So if while you're tracing through the tree, each node is made to point at its grandparent, it won't compress it all in one step. But it's only adding one line of code to the find algorithm. Right? That maintains maximum flatness. And flatness is good. Any questions? All right. See you, folks.